Hello everyone. Today I want to go over the homework assignment that you just completed, which was watching section 6 with a gentleman by the name of Harry Wright. Harry wrote G-code and he had you complete a portion of it, and the shape that he was trying to create was just this arbitrary shape here. There was actually 6 videos. The first 5 videos went over something called can cycles, where we use these single line commands to remove material. And section 6 is the section that you guys were involved with, where you interacted and you completed this path contour. And in the end, what we were trying to accomplish was having this shape protrude outward from the part. I have a sample. It's not that particular shape, but you can see that this particular shape is protruding out from the block. I want to go over the G-code a little bit deeper for a couple of reasons. One, for your understanding, and two, for your final exam, there's going to be about 70% of the questions taken from this lecture. So I may talk a little bit fast because I don't want this video to be too long, but let's get started. First thing I want to talk about is, what is G-code? G-code stands for geometric coding. There's kind of like conflicting stories that I read and researched about how it got started, but it was back in the 1950s, and there's 2 entities taking credit for creating G-code, MIT and the DoD, Department of Defense. So let's just give credit to both, because I really don't know which one of those 2 or whether they work together to develop it. G-code in itself was developed in order to automate machines, CNC machines. CNC stands for computer numerical control. And so the machines that we use today that have computer controllers on them that control their movements, most of them, if not all of them, use some type of coding like G-code. G-code, for the most part, is a universal code. However, there are certain parts of G-code that are proprietary to the machine builder, the person that makes the controllers that are out there. So let's go over some of the basic format rules for G-code. G-code, if you notice here, and by the way, if I'm standing in front of it blocking it, you can follow along with your homework sheet. Just print that out and follow along with it. But G-code, for the most part, is a capitalized code. In other words, when you write G-code, it needs to be capitalized. There are newer controllers out there now that use the Linux system, and I've seen some of these computer, I'll call them PC-based, where you can use upper and lowercase. But a lot of the professional controllers that have been out there for years and years and years require the G-code to be all capitalized. The other thing is when you are writing G-code, it's important that you write it in what's called an ASCII-based editor. You can't use something like Word or Excel because they have fonts, and those fonts are created by little control characters in the background. Makes the font look pretty, like Times New Roman and italic, but to a computer controller, a CNC controller, it confuses it. So we use these editors, like Notepad is a good one that comes with Windows, or the editors that come with the actual software like Mastercam and SolidCam. There's a lot of makers out there that have these ASCII-based editors specifically for G-code. Besides the fact that G-code needs to be capitalized, the other thing that you'll see with G-code is that the very first line of G-code is typically called our initialization line. What it does is it sets the machine up in the modes that it needs to be. For example, this first line here is telling the machine that it's going to be in rapid mode, meaning that all movements are going to be moving as quickly as possible, as fast as that machine tool can go. The second one tells it that it's working in an absolute coordinate system, G90. That means that all the points that the cutter is going to go to, that we reference, are going to be referenced from this origin here. If we had switched it to G91, that's incremental or delta moves, and then every point would be referenced from its previous point. G70 in this case is telling it that it's going to be in inches. G71 would be millimeters. G40 turns off cutter compensation, and we'll talk about that a little bit later. And then there's a feed rate statement in here. Without a F statement, a feed rate statement, the movements that the cutter makes when it's engaged in the material wouldn't happen. It needs to know how fast to travel. Now there are 4 basic movements that we can do with the G-code, and they're listed right here. G00 is rapid, and like I said, that moves the machine tool as fast as can possibly go, and that varies depending on the machine. We have machines in this machine shop that can move just about 110 inches a minute, 590 inches a minute. Our lathe over there hits a little over 1,000 inches a minute. So That is when the tool is not engaged in the material and you're just trying to get it from point A to point B. These three, G01 is a linear move, and that means it can move any straight line, whether it's be a horizontal or a vertical or any angle in between. A clockwise arc, G02, or counterclockwise arc, G03. These three require an F statement, and they don't require an F statement in each line. We'll talk about what modal codes are in a moment, but they require a feed rate value in order to know how fast it needs to travel, because we use these three when the cutter is engaged in the material. So let's liken this to SolidWorks or AutoCAD that you're used to using. What do you use those to make your extrusions and your cuts? You typically take lines and you take arcs and you trim them together to make some type of a shape, and then that becomes your cutting extrusion tool. Well, it's the same thing here, except in this room of subtractive manufacturing, we combine these lines and arcs, and then we use the Z depth of the cutter to push the cutter into the material to cut the depth that we desire. The next thing that we'll talk about with the G code is the order that G codes need to be in. These are, we always kind of call them lines of code, but they're actually considered blocks of code. And by that, I mean that the computer controller looks at this entire block of information. And therefore, it does not have to be in a specific order, meaning that X does not have to appear before Y, Y does not have to appear before Z. In these two can cycle examples, look at this one here, you'll see that the X and the Y, and then there's an H and a Z, and then down at this one, they put H first, then Z, then X, and then Y. So it doesn't matter, as long as what you want to have happen in that block is in the block, the computer will sort it out. Lastly, the code itself, most of the codes are what we call modal codes. And what's a modal code? Modal code is like a light switch, which means that when you turn a light switch on, it stays on until somebody walks over and turns it off. The same with these G codes. And for that reason, you don't have to repeat the G codes in every line. Like previously when I was talking about the feed rates. If you notice here, in this subprogram, when Harry was writing this shape, he does not include any F statements. He has an F statement up here, so once that switch was turned on, he did not have to repeat the F statement. And here's another move where the G01, a linear move, was actually turned on, and it moved to an X.3 dimension, or position, and then it went to X.8 and then Y2.06. All three of these moves were linear moves because this switch, the G01 being modal, was turned on, and then what turns them off is an opposing code. So now G03 was turned on, which turns off G01, and then G03 gets turned off when G01 gets turned back on, and that's what modal codes are. The end block numbers. End block numbers are like place markers. They are not necessary in order for the program to run. Okay, and I'll repeat that, they're not needed. However, we like to have them because they're great reference points. When you consider that programs can get quite lengthy, and a lot of the code looks identical, and some of it actually is identical, it's just going at different depths because it's repeated. Imagine running a part, a large part, where the tool is going to run for maybe a couple of hours in that part, and somewhere along the way the tool dulls or it chips or it even breaks, and the operator that's running that machine needs to pause the machine and fix that problem. So they stop the machine, they look at the end block number where they left off, and then when they change the tool and recalibrate it, they can start back where they left off. Without those end block numbers, that person would most likely start the program from the beginning because they didn't know where they left off, and of course that would cut a bunch of air up until the point where the tool broke again, and that's just not efficient. So that's kind of like the basics of the G-code formatting. In this particular case, you guys did not have to watch videos 1 through 5 in order to complete the assignment, but just as a reference, these lines, or this block and this block, do two different types of operations. Now this G77, which does a circular pocket, it actually had a circle in your original drawing here, and it took the material from the center of that circle out. It had a rectangle drawn in here and a rectangle drawn in here to remove material. That was all done in a single line command, and each one of these variables told it what the diameter of the tool was, how much it needed to step over, what the step down was, and also the feed rates to rough it at, to finish it at, and when it was doing its finished feed rate, how much stock it had left in order to do that finished cut. Same with the rectangular cut. These can cycles are proprietary to this particular controller, which in this example, when it was written for an analam controller. So certain codes are universal, like these, but some of these are just proprietary to that machine controller, but they all share the similar, I'll say, functions. They just may have a different code that calls them out. So one of the things that I want to call out to you guys here is the formatting. In the beginning of this program, from the beginning to the M2 is the reset command that ends the program and rewinds it. We call it a rewind, which was M30 way back in the day. But what we've done with this is this will send it back to the beginning. Notice that the program continues on from there. And I've divided this up from the beginning of the program to the M2 is considered the main portion, the main part of the program. It controls and it can call out these subprograms. On the analam controller and on most controllers, these subprograms can exist, and sometimes we can even nest them, meaning that we can have a subprogram within a subprogram. And these subprograms are identified by a label that begins with the letter O and then some type of a number. For the analam controller, that number range was from 01 to 09999. So that's how many subprograms can exist that a main program can call out. And the way that it works is as the main program is running and executing its commands, the command of M98P5 tells it to call a subprogram, program 5, and that's the one that's going to actually call. It doesn't have to call 1 and then 2 and then 3. It can call any one of the labeled subprograms that are below it. So what happens is the controller then leaves the main program and searches down through the other list of programs, so it finds program 5 and then executes all the movements in 5. Once it gets to the M99, which is the end of subprogram command, it then leaves that subprogram, goes back to the main program to one line after where it was called, and then it executes from the main program again. And in this case, it moved the cutter down a little bit deeper and then called the subprogram a second time, which then made it go out of the main, find the subprogram, go back down and then back up, and then it finished the program with the M2. What is the purpose of subprograms? Subprograms make a more memory efficient program. Way back when, back in the 1950s and even the 80s and 90s, when machine tools came, they had very little memory. Memory was very small, memory was also very expensive. And so we had to get creative. They had to get creative when they created these codes in order to make more efficient ways of using that small amount of memory. And so one way to do that was to create these subprograms. And in this case, in this example, this contour was cut twice, one at 50 thousandths depth of cut, one at 100 thousandths depth of cut. So rather than making a longer program and also maybe possibly creating a mistake by creating the program once and then writing more code, you can write that subprogram that does that shape, and you can call it multiple times through the main program, and it will give you a more memory efficient program, and it also helps eliminate possible mistakes. You can also edit the program a lot easier. Any change that I make to the subprogram will be carried through no matter how many times that subprogram is repeated. So again, to repeat, the main purpose of these subprograms is to make a more memory efficient program. Today's machines have tons of memory. Our newest machines, our Tormax, came with 85 gigabytes. Our 1995 Fidel came with 128K, not megabytes or gigabytes, but K. So this is a more efficient way of running it. After the initialization line that sets the machine up in its modes, we have a tool call out here. And what the T command does is it calls out the particular information for the tool that happens to be in the spindle. So what I'm giving you here is 3 examples. We have a centering drill, which is also called a spot drill. We have a regular drill, it drills a hole. And we have something called an end mill, which we use to trim the outside edges of parts and also what cut this profile. Now, each one of these, as you notice, is in a tool holder that ends up mounting into the machine, but notice that each one from the bottom of the tool holder has a different stick out length. It's sticking out of that holder at a different length. For the CNC controller, for us as programmers to control that cutter, we take two pieces of information from this particular tool number and we enter it into the machine in something called the tool offset page. It looks like a spreadsheet. It's got a column for the tool number, a column for the tool's diameter, a column for the tool length, which is this particular length of each one of these tools. When the tool is called up in the program, again, it's a modal switch, so it turns on, it reads that information. What is the diameter of this tool? What is that tool's length? And it applies it to every move that you program. So you as the programmer are only programming these little tiny blue dots, which is the center line of the tool and the tool tip. And you're driving that from this center line over each one of these points, either in a G01, a G01, a G03, and as you walk around the part. So it's pretty simple to program, but that is the purpose of tool offsets and what happens when it calls a tool. What cancels a tool call out is another tool. So when tool 4 is called out or tool 5, it turns off the previous tool call out, just like the movement commands here also change that. All right, so moving forward here, the main part of the program in this particular example was roughing out the part and then calling the subprogram. This is the portion where you had to finish the 13 lines of code to complete that particular part. So let's kind of go over what's happening here. So first, the tool began at an X negative position, X negative 0.5, Y 4.7. So the tool, let me grab a different color marker, is going to go from here, that negative position, to this point right here. Then the next command tells it to move to X 0.8. That's going to put it over here. Remember, we're driving the center line of the cutter. And the next move tells it then move to Y 2.06, which puts it over here. But notice that if we're driving this cutter from its center point to each one of these points, we're going to end up taking away the material we want to keep. So what we need to do is invoke something called cutter compensation. And what cutter compensation does is it offsets the cutter either to the left or to the right of the contour. So that's what the purpose of cutter compensation is. So in this case, if you notice, in the line that says G01 X.3, the first move to this point, there's also a G41 that's placed in that line. And G41 stands for cutter left or climb cutting. It's also a preferred method of cutting because it gives us a better finish. G42 is cutter right, and G40 is cutter compensation cancel. That's when the tool will, in fact, run right over the center of these parts. So, a couple of rules about cutter compensation. One, how do we determine what is cutter left and what is cutter right? And two, when do we use it and how do we use it and which one should we use? Well, let's just draw a simple shape here, right? Something that looks like this arbitrarily. What you need to do in order to determine whether you're cutter left or cutter right is pretend you're the cutter, or that you're sitting on top of the cutter. So let's draw a cutter here, and let's put the direction of travel here. So if this is the cutter and it's moving in this direction, and you're pretending that you're the cutter, we'll put a couple eyes on here and a nose, you need to look at where you are, you being the cutter, in relationship to the part. So this little guy right here is heading in this direction. He's on the left side of this line. So therefore, he is at G41, which is cutter left, also called climb cutting. As he moves this way, in this direction, he's still on the left. And when he moves this way, in this direction, he's still on the left. So in other words, as long as he continues to move in the same direction, the cutter compensation remains the same. And therefore, once it's turned on like a light switch, it does not need to be repeated in every single line that we have. If we were to change this arrow and move it to this direction, now, remember, you're the cutter looking the direction you're traveling, what side of the part are you on, or the line you're cutting. Now we're cutter right, and this is G42. That's called conventional cutting. And there's a reason why we use either of those. But I want to kind of go over first what happens with cutter compensation. cutter compensation doesn't just occur. In other words, a lot of times the cutter's already engaged in the material, and what we don't want to have happen is that when we turn on cutter compensation, the cutter immediately moves left or right. That could destroy the cutter. It could interfere with a part of the contour part that it could violate, let's say, a wall of the part. So cutter compensation requires what we call a ramp-on move and a ramp-off move, a distance of travel. And the distance that cutter needs to travel in order to engage cutter compensation properly has to be greater than the tool's own radius. And what happens is, in this case, where the cutter was sitting at x negative 0.5, it now is going to go to x 0.3. And when it goes to x 0.3, it begins this movement of slowly moving to the left of this particular point, and the computer calculates where it needs to go so that when it gets to that point, the cutter is tangent to the point. And once cutter compensation is activated, the cutter stays tangent as it moves all the way around. That way you as the programmer only have to program to the points that you know, and the actual cutter, the computer will keep it tangent all the way around that contour, and thus giving us that profile that we want that's protruding off the part without violating the part. So once cutter compensation is enacted and we come all the way around the part, we need to turn cutter compensation back off. That puts it back on the center, and that move is called a G40. G40 will now take that cutter and send it off the part. So that's kind of what the rule for cutter compensation is. Again, just to repeat, what cutter compensation does is it allows us to move the cutter to the left side or the right side of the profile. So now that you have that concept in mind, the next question occurs as to, well, which one should I be using? Well, as I said, the preferred method is G41, which is climb cutting. It gives us a better finish. But can we use climb cutting on every type of machine and in every scenario? Absolutely not. There are certain machines out there, especially the manual mills that we have in the student machine shop and that you would use in this machine shop, that using climb cutting with a large enough cutter and a big enough cut can cause a dangerous condition. I like to call it runaway table because that's exactly what happens sometimes. What happens with climb cutting, and the reason why it's called climb cutting, cutter left, is if you think about the cutter, it's rotating in a clockwise direction, and there are cutting flutes or teeth on this cutter that bite into the material to shear it. So when this is rotating in a clockwise direction, it's like a wheel, and it wants to drive over the part. So what happens in a condition with cutter compensation that can end up being dangerous and seriously injure you is if I come over here and I draw another part that looks like this, and we use the scenario of cutter compensation, cutter left. So let's say this is a big 1-inch cutter and it's got 6 flutes to it, and we want to chop off all of this material with it. Well, if you think about it, this is not doing 1 RPM or 2 RPM. A 1-inch cutter, and let's say soft aluminum, can be running at a couple hundred RPM. And as soon as that cutter engages in the material, it's going to bite into it. And when it bites into it, it's going to take off running. And when it takes off running, if your part's not securely mounted in the fixture or in the vise, it's going to throw that part at you. But because these cutters are also made out of very hard materials, typically what happens is the cutter can't withstand that type of force that's being placed on it, and it can shear or break, and sometimes those pieces can fly right back at you. And I've even seen on looser tables where there's play in the table, where the table actually makes a leap. It runs away from that person, and that just amplifies the problem. So in order to get around that, we use the conventional cutting method, cutter right, to take these larger cuts. So let's take the same cutter, same size diameter, same teeth, same rotation, and same direction of travel. But in this case now, when it's trying to cut all this material, instead of it wanting to roll and drive into the part, it wants to roll away from the part. So you, on a manual mill, you're controlling that cut, and it really has nothing to bite back into, because as you're forcing it, maybe that's not a good choice of the word, as you're feeding it into the material is being taken away, so it has nothing to bite on to run back at you. So it's a safer way to cut larger pieces of material off but of course that leaves kind of a not as good of a finish. So then we can come back with a lighter cut and climb cut it, and we won't have that situation happen because the cut is so light that you're in control of it. Now on CNC machines use a different type of lead screw system. They use what's called a ball lead screw, and they're also attached to servo motors. And those servo motors can beat us all in an arm wrestle. It holds that machine at a very, very steady, rigid rate. And the other thing too is that when we're on manual machines, we're human and we're turning the crank, and as smooth as we try to be, we're never going to be as smooth as a motor that's being controlled by a computer. So all of those things play into whether you end up with a harmonic or an uneven cut, and the fact that the computer can hold on to that perfect feed rate, and the servo motors can drive it at a nice smooth condition. We can actually climb cut heavier cuts on CNC machines where we wouldn't attempt it on manual machines. So that's kind of the rules behind cutter compensation, what cutter left is, what cutter right is. Also, one of the things about cutter compensation is that you don't always have to use it. There are certain situations where cutter compensation isn't being used. In an upcoming assignment, you'll be doing some engraving, and when you're engraving, you'll have cutter compensation turned off because you're going to engrave, let's just say, your name into something, and so you might just drop the cutter right here and just want to run right down the center of it. So for that reason, you don't need to apply cutter compensation. The next thing is when the tool is traveling through the material. Remember I said these three moves when it's in the material require that F statement, a feed rate. So what is a feed rate? Well, a feed rate is exactly what it implies. It's a rate of feed that cutter is going to be traveling through the material, and that's based on a formulation that we have. So the best scenario that I can give you guys about metal removal rates and feed rates is one called cars, trucks, and roads, because it's kind of easy to relate to. So we all know what a car is, right? We know there's different types of cars. You have your base model like Toyota Corollas, and you have your more sophisticated suspensions on your BMWs and your Corvettes, a little bit more horsepower on some of those things. We know what a pickup truck is. Pickup trucks generally have higher ground clearance, and some of them come in two-wheel drive and four-wheel drive. So let's take those three vehicles. Let's take a Toyota Corolla. Let's take something like a Corvette that has a nice suspension package to it, and let's take a pickup truck. And let's take it down a standard road that's paved and straight and flat. All three vehicles are equal. They can travel the posted speed limit. Let's say the speed limit's a highway and it's 70 miles an hour. We have no problem pushing all three vehicles down the road at that rate. It's when the road condition changes that now the characteristics of each one of these vehicles begin to show. So for instance, let's just say now that road condition changes to a very windy road. Let's say like the Pacific Coast Highway on the west coast of the United States, where the road is like hairpinning a lot and you're trying to maintain a set speed. Well, that Toyota Corolla isn't built with a suspension package, and you're going to kind of feel a roll effect on that. You're not going to be able to handle those road conditions quite as easily as, let's say, the Corvette, which has lower ground clearance, better suspension, stiffer. It's kind of tuned up in order to hug those curves. And of course, the pickup truck is not built for that either. So the clear winner becomes the Corvette. And when we go off-road, and now we're on, where there's rocks and dirt and maybe some hills, now that higher clearance on that pickup truck, especially if it's a four-wheel drive, where the gravel might be looser or the road conditions are looser, it has more bite into the road, and the pickup truck becomes a clear winner. Well, those different vehicles, those different cars and trucks are our cutters. And those roads that they're traveling on are the materials that we travel on. And in order to control those, we have to drive each vehicle or cutter at a certain rate through a certain type of road condition. For instance, 70 miles an hour down a flat asphalt road, fine. But when we're going off-road, I don't think we're going to be doing 70 miles an hour, right? We're going to have to slow that down and use as caution as we're going over these different bumps and rocks. So we have these formulas that we can calculate for not only metal removal rates, but to calculate the RPM, how fast that cutter should spin, and how quickly it should travel across that material. One of the things that you're going to have on your quiz is for you to calculate the RPM and feed rate based on either a scenario or I'll give you the parameters. So this chart, you'll be able to find it in the first day handouts on the website. And you're gonna need it to reference to because it's got the formulas that you need here. It's got a chart here giving you different types of materials. And we have these two columns here. One is called surface feet per minute, which is also abbreviated as SFM, and feed per tooth, which is also abbreviated as FPT down here in the formulas. So the first thing you always want to calculate is the RPM, because you're going to need the RPM. That's going to tell you how fast to spin the cutter. And then you're going to use that RPM that you calculated into the inches per minute feed rate, which is exactly what it means. It's how many inches that cutter will travel per 60 seconds every minute. So by using these simple formulas, you can calculate the baseline for what these cutters are. Now, when you calculate this, just know that in real life, this is a guideline, and these charts vary depending on the manufacturer of the tool, the style of the tool. The best place to get this information is from the actual tool vendor, because they may have a tool that has a special coating on it, or maybe it's got a different geometry, a higher helix on the flute, and they might be able to go a lot faster than what these charts are. But whatever these charts say, that's your baseline. What do I mean by that? Well, let's go back to the cars, trucks, and road scenario. Supposing that all three vehicles are traveling down, let's say a turnpike, at that 70 miles an hour, and then all of a sudden, you know, the skies open up and we got pouring torrential rains where you can't see 2 feet in front of your windshield. Are we gonna continue to do 70 miles an hour? Of course not. We're gonna hydroplane, or we could wreck into somebody, or somebody could wreck into us. We're gonna lose control of that vehicle. Well, the same thing happens in the material. That baseline that you just calculated is under perfect conditions, meaning that you've got the sharpest cutter, using the best type of machine in the most rigid setup. If any of those conditions vary, maybe your part's got some thin areas, or it's hanging off the vise a little bit, or your machine's not quite that new or tight, those are gonna cause you to have to slow down just like you would on the highway. So you kind of adjust the feed rates and the RPM in order to do so. And one of the ways that we do that on machines is the cutters will generally talk back to us. When that cutter that you engage into the material starts squeaking, and it's squeaking and kind of yelling back at you, that tells you that the cutter is spinning faster than it's removing the material. And you have to do one of two things, either slow down the RPM or increase the feed rate. If the cutter's growling at you really, really loud, well, that means that now you're pushing the cutter harder than it can go, and you need to either increase the RPM or decrease the feed rate. So those are kind of signs that we use when we are cutting in certain materials. And then there are certain conditions where our harmonic just builds up, because maybe you have a thin area and getting out of that squeak or that roar condition is really, really difficult. And that's just, it depends on the scenario that we're doing. But the cars, trucks, and road scenario should help you understand the feeds that we need to travel around these parts. And as we travel through this particular contour, we're using the different codes. So when you traveled around this particular shape here, we used a G01 to go to this point, a G01 to go to this point, a G03 in order to go counterclockwise, G01 to go straight again, G02 clockwise, G01, G02, G01. This is a G01 and a G01, which, by the way, we don't have to repeat the command G01 because it's a modal code. G03, G01, G03, G01, G02, and then a G01 with a G40 to take us back to the home position or start position. We always want to turn off cutter compensation before we lift it out of the part. Now, it's perfectly legal to lift the cutter up and leave cutter compensation on. I just don't advise it because it is on, which means that if you want to come back down inside here to do some other work with that cutter and you tell it to come down right here, well, it's not going to come down right here. Based on the next move that it sees, because it has what's called block look ahead, it's going to move to the left or to the right, depending on which cutter compensation is invoked at that time. And that cutter could hit and violate part of that part that you don't want it to hit. So it's just good general practice that when you turn cutter compensation on, turn it off with a ramp on move before raising the cutter up and moving it to another part of the part. So that's basically the whole G-code scenario. The only other thing for the analam controller, and again this is proprietary, is that these arcs for the analam controller, if you noticed in your homework, you had arcs that had I and J's, and you had arcs that had just regular R commands. That is, again, proprietary to the analam controller. Not every controller has to have these rules, but for the analam, anytime an arc swing, and in this case, the very first arc swing was 180 degrees. The center of the arc was here, and it swung 180 degrees from this point to this point. Whenever that arc was greater than 90 degrees of a swing, the I and J had to be used. And on an analam controller, the I was just simply the distance in the X direction from the origin of the part to the center of the arc, and the J was from the origin of the part to the center of the arc in the Y direction. Now, some I and J values, depending on the machine, use what's called an incremental value, and it's actually a distance from the start of the arc to the center of the swing, but we won't worry about that right now. That's control dependent. But on the analam controller, just to explain the homework a little bit deeper for you guys so you understand why there were I's and J's and R's, these arcs here that were only 90-degree swings followed the rule for the analam that said anything less than or equal to 90 degrees can use an R, and the R was simply just putting into the line of code whatever that radius is. And in this case, it was a 0.5. So you'll see that after it did the G03, and it moved G01, and it came back up, the very first arc that I just labeled was a 0.5 radius, and it used a G02 and a 0.5. So that's just to explain the difference between the arcs. So coming up, you're going to be writing a program for CAD/CAM, because that's what we use next in this class. But this hopefully explains to you what we need to know for the G-code itself, the rules that it follows, and also pay attention to what I said, because you're going to find that this will repeat itself on your final exam. Rules about cutter compensation, the difference between cutter left and cutter right, how we determine cutter left or cutter right, what is the bad scenario that can happen, what are tool offsets, what is that initialization line, whether we need end block numbers or not, why do we have subprograms and what are they, what do they do for us. And then the general format of coding, you'll have a list of codes on your exam that you have to find the definitions for and write the definition and the proper code it to match it to the proper definition. So these are things that I wanted to cover for you. Hopefully this explained it better than that first video. And that really concludes this lecture.